Confidence is not reliability. A model can achieve near-perfect error ranking, hit benchmark dice scores, and still be dangerously overconfident in the exact voxels that dictate patient survival. That's the central finding of recent research on Monte Carlo Dropout in brain tumor segmentation. Today, we're breaking down why standard uncertainty metrics are failing us in clinical AI, how to properly evaluate calibration, and why subregion-specific analysis isn't optional, it's mandatory. Glioblastoma remains one of the deadliest primary brain tumors. Treatment planning hinges on precise multiparametric MRI segmentation, specifically delineating the whole tumor, the tumor core, and the contrast-enhancing tumor. The enhancing tumor region is spatially small but clinically massive. It drives chemotherapy response assessment, guides stereotactic biopsy targeting, and directly impacts RANO criteria evaluation. Deep learning models now approach expert-level performance on benchmarks like BraTS. But they output a single, deterministic point estimate per voxel. No confidence signal. No warning system. If the model mislabels the enhancing tumor margin or infiltrative edge, it does so silently. In medicine, silent errors aren't just statistical noise. They're patient safety risks. To bridge this gap, researchers turn to uncertainty quantification. Specifically, Monte Carlo Dropout. You've likely seen dropout as a regularization technique during training. But Gal and Garamani demonstrated that if you leave dropout active at inference time and run multiple stochastic forward passes, you're effectively sampling from an approximate posterior distribution over the model's weights. Each pass applies a random channel-level mask to intermediate activations. By averaging 20 passes, you get a predictive mean and can compute voxel-wise uncertainty. The variance across passes captures epistemic uncertainty, gaps in what the model learned from the training data. The study evaluated this on two architectures using the BraTS 21 test set of 126 patients. First, a high-performing pre-trained SegRes-Net with post-hoc dropout injection. Second, a locally trained UNet-Trace with embedded dropout, providing a theoretically cleaner baseline and a lower-performing regime to stress-test calibration. But how do you actually measure whether the uncertainty is useful? The standard approach uses predictive entropy. For each voxel, you compute the Bernoulli entropy of the average sigmoid probability across the 20 forward passes. High entropy means the model is uncertain. To see if uncertainty actually flags errors, researchers use AUROC, treating erroneous voxels as the positive class and entropy as the ranking score. An AUROC of 0.97 sounds exceptional. It means uncertainty correctly ranks most errors above correct voxels. But here's the critical limitation. AUROC only measures ranking quality. It does not capture whether the predicted confidence values are actually calibrated to empirical reality. A model can rank well, but be wildly miscalibrated. That's where expected calibration error, or ECE, comes in. ECE measures the average gap between predicted probabilities and actual accuracy across probability bins. It's computed on foreground-relevant voxels, excluding the massive background class that would otherwise skew the metric, since over 98% of voxels naturally fall below low probability thresholds. Now let's look at the results. Both models achieved near-identical AUROC scores, around 0.975. On paper, they're equivalent, but the calibration analysis reveals a stark divergence. SegRes-Net showed moderate, consistent underconfidence across all subregions. Its reliability curves sat cleanly above the diagonal, and predictive entropy correlated positively with segmentation error. When the researchers stratified patients by entropy quartiles, the high uncertainty group had a median whole tumor dice of 0.835, compared to 0.925 in the low uncertainty group. That's a clinically actionable triage signal. It translates voxel-level uncertainty into a deployment-ready patient-level review trigger. UNet-Trace, on the other hand, exposed a critical failure mode. Its whole tumor calibration was respectable, but its enhancing tumor region was catastrophically miscalibrated. ECE hit 0.915. The reliability diagram was almost completely flat at an observed fraction positive of 0.4, regardless of predicted probability across the full range. In practical terms, the model's ET probability outputs carry zero discriminative information about true voxel status. Worse, the mean predictive entropy for ET was 0.054. Near zero. That means the model is aggressively overconfident, even when it mislabels 40% of the enhancing tumor voxels. High AUROC completely masked a calibration collapse. This dissociation between ranking quality and calibration validity is why AUROC alone is insufficient for clinical deployment. In dense segmentation tasks, erroneous voxels constitute a tiny fraction of the total volume. Even a weak uncertainty signal can achieve a high AUROC by correctly ranking a handful of errors above the massive pool of correct voxels. But clinically, we care about absolute reliability. If a model assigns near-zero entropy to a severely miscalibrated enhancing tumor, it cannot support safe semi-automated workflows. Radiologists need to know which cases genuinely require review. SegRes-Net's entropy-based triage does exactly that. UNet-Trace's signal is informationally invalid on the most treatment-critical subregion. The model achieves competitive whole tumor overlap while being systematically overconfident where it matters most. Of course, this study has defined boundaries. Evaluation is limited to a single publicly available dataset with consensus labels. The 20-pass MC dropout approximation wasn't stress-tested for pass count sensitivity, and post-hoc dropout injection into seg-res-net introduces a theoretical asymmetry compared to the embedded dropout in UNetRes. Future work must incorporate multi-site data, apply calibration techniques like temperature or Platt scaling to reduce ECE, and conduct prospective reader studies to measure actual radiologist efficiency gains with uncertainty overlays. The takeaway is clear. Strong uncertainty error alignment is necessary, but not sufficient. Confidence is not reliability. When selecting segmentation models for clinical deployment, you must evaluate subregion-specific calibration. Report ECE, plot reliability diagrams, and analyze entropy magnitude alongside AUROC and DICE. Uncertainty quantification isn't just a theoretical exercise. It's a practical triage tool, but only if it's properly calibrated. If you're working in medical AI, or just interested in how we bridge the gap between benchmark metrics and clinical safety, I highly recommend reading the full paper. It's a rigorous blueprint for model evaluation that goes far beyond overlap scores. Let me know in the comments how you're handling calibration in your own uncertainty estimation pipelines. And if you want to dive deeper into the Bayesian foundations of MC dropout and epistemic uncertainty decomposition, check out the linked resources below. Thanks for watching.